Thank you. Thank you so much for tuning in. This is our third topic, our third lesson, sorry, on radioactivity. This is the third lesson on radioactivity. And in this lesson, I'm specifically going to deal with the radioactive detectors, the radiation detectors, sorry. And the detectors are actually something that we can use for us to be able to show the presence of a certain radiation. What can be used to prove that a certain particle is emitting either alpha, beta, or gamma. So, onto my first detector, that is the photographic emulsions. All the three radiations affect photographic emulsions or plate. Photographic films are very useful to workers who handle radioactive materials. These workers are given special badges which contain a small piece of an exposed photographic film. If during the time it had been worn, the worker was exposed to radiations, it should darken on development. Underline, it should darken on development, implying that further safety precautions should be taken. So basically, this is what it means in a nutshell, that you're having a photographic film, and the photographic film can be compared to the piece of paper that they normally use to get the X-ray images. So if you have a paper like that, mostly the paper is normally brownish in color. So just in case you have a photographic paper, or rather photographic film, and then we have some radiations hitting the film, the paper is expected to darken. And if there are no radiations, the paper remains the same way it was, before it was exposed to any radiation. And from the statement we are having here, most of the people, the workers that work with such radiations, they're normally given special badges, and these badges normally contain a very small piece of an exposed photographic film. So at the end of the day, after these people have worked, if it is noted that the film darkened, then it means that they were exposed to the radiations, and this will call for further precautions. Then onto the second detector. The second detector is the gold leaf electroscope. And the gold leaf electroscope is not very new to us. The gold leaf electroscope was introduced to us in Electrostatics 1, a topic in Form 1, whereby we noted that if an electroscope is neutral, the leaf does not diverge. The moment the electroscope becomes either positively or negatively charged, the leaf is expected to diverge. And the extent to which the leaf diverges depends on the quantity of the charges. So if the charge is less, and then it is increased, you expect the divergence to do what? To increase. And if the charge is more and it is decreased, we expect the leaf divergence to do what? To decrease. So therefore, when we use an electroscope as a detector, or as something that can help us to show whether there is the presence of such radiations, will require a charged electroscope. How does it behave? A charged electroscope loses its charge in the presence of a radioactive source. Why is that so? When we have a radioactive source placed near the cap of the electroscope, this source ionizes the air around the electroscope. When the charges are ionized, that is the positive and the negative charges in air will separate. And on separation, the ions on the opposite charge to that one of the electroscope will be attracted to the cap and eventually neutralize the charge of the electroscope. So using the formula, using the diagram that I have here, I can explain this in a nutshell. So this is an electroscope that is positively charged. Then we have a source of radiations. Here, the source of the radiations. When radiations are emitted, the ions in air, the charges in air separate. So when they separate, this one results in both positive and negative charges. Because our electroscope is positively charged, it is going to attract the negative charges from the basic law of electrostatics. So when the negative charges are attracted, these negative charges neutralize some of the positive charges within the electroscope. Then the number of positive charges are going to reduce, and as such, the divergence of the gold leaf decreases. In simple terms, what it means is whenever you have a radioactive source being placed near the cap of an electroscope that is charged, we expect the gold leaf to do what? The divergence of the leaf to decrease. And if the source that is put at the cap of the electroscope is not radioactive, there will be no effect on the divergence. A very important point to note here, as a detector, a charged electroscope is not suitable for detecting beta and gamma radiations because their ionizing effect in air is not sufficiently intense, so the leaf may not fall noticeably. Thank you. That is what I can say on the electroscope. Again, in case of a question, feel free to ask. Then we have another detector, the one that you are referring to as the cloud chamber. Whenever we have air being cooled until the vapor it contains reaches saturation, it is possible to cool it further without condensation occurring. Under these conditions, the vapor is said to be what? Supersaturated. This can only occur if the air is free of any dust, which normally acts as nuclei on which the vapor can condense to form droplets. Gaseous ions can also act as a nuclei for condensation. The ionization of air molecules by radiations is investigated by a cloud chamber. So there are two types of cloud chamber. We have the expansion cloud chamber and the diffusion cloud chamber. I'll go through the two chambers with a lot of clarity for us to be able to see how a cloud chamber can be used as a radioactive detector. So the cloud chamber is the one as represented here, but its cross-section can be shown here. So this is the cloud chamber itself. So for from the cross-section, we can see that the radioactive source is normally put on one side of the chamber. Just next to it, there is a screen. There is a dark screen that is placed next to it. And then there is some vapor here. Of course, this is a piece of glass and there is a piston. So what have we mentioned? That alpha, beta, and gamma normally causes ionization of the air particles. That is, they are able to separate the negative and the positive charges within air. So if this is a radioactive source, this source will emit some radiations. When these radiations are emitted, what happens is that they ionize the air within the chamber. And if it happens that this piston here is moved downwards, the air within the chamber will be forced to expand. And anytime the air expands, it normally cools. So this air within the chamber will cool. When it cools, it will also make the vapor within the chamber to also cool. So if this vapor cools, and then at this point it meets the ions. due to the ionization of this radioactive source, what happens is that this vapor will condense on the ions. In the absence of these ions, this vapor will not condense. And if the vapor condenses, it forms some whitish lines that they're referring to as what? Tracks. So during a study like this, if we have a particle being put on at this point, and some tracks are formed, then it shows that that is a radioactive source. If there will be no tracks formed, then it implies that the source that was put here was not radioactive. Again, depending on the way the tracks that will be here will appear, then this radioactive source can be termed to have produced either alpha, beta, or gamma, depending on the way the tracks will appear. Allow me to explain something about the tracks that will be formed for different radiations later on within this lesson. So basically what I've talked about, I've given it to you here. When a radioactive element emits radiations into the chamber, the air inside is ionized. If the piston is now moved down suddenly, air in the chamber will expand and cooling occurs. When this happens, the ions formed act as a nuclei on which the saturated alcohol or water vapor condenses, forming what? Tracks. Thank you for that. You can pause the video for you to be able to copy down very important things within this topic. The next cloud chamber is the diffusion cloud chamber. And I want us to note the parts of the diffusion cloud chamber. This one is in two compartments, the lower and the upper compartment. Within the upper compartment, we have the perspex lid. Perspex is just a special kind of glass. We have a filtering soaked in alcohol. We have a light source and a black velvet chamber floor. Then there is some dry ice. There is a sponge. There is a leveling wedge. There is a removable base. And lastly, a cork onto which the radioactive source is normally put. So each and every part of this chamber serves a very important role. Serves a very important role. I've minimized that so that as I talk about a certain part, you can confirm from the diagram. So one of the parts I've talked about is the dry ice. Dry ice will cool the blackened surface, making the air on the lower surface of the chamber to be what? Cool. So basically, because of the presence of the dry ice, the temperature on the lower compartment is cool. Then the sponge, it ensures that the dry ice is in contact with the blackened surface. We have the wedges. The wedges keeps the chamber horizontal. The light source illuminates the tracks, making them visible. And lastly, the blackened surface provides a better background for visibility of tracks. Remember, on the other chamber, not the chamber, yes, on the other chamber, we had a dark screen. That is on the expansion cloud chamber. We also saw a dark screen. The dark screen serves the same purpose as the blackened surface, providing a better background for visibility of the tracks. So how does this diffusion cloud chamber, how is it used for it to be as a detector for the radioactive the radiations from the radioactive particles? Sorry for that. The alcohol from the filtering vaporizes. This alcohol here will vaporize and diffuse towards the black surface. This vaporizes and then diffuses to the black surface. Radiation substance, this one, radioactive substance, emits radiations which ionizes the air. Just like for the other chamber. Sorry, let me share the screen again. So just like the other chamber, when you have radiations coming from this source, it will ionize the air around this place. When the air around this place is ionized, there are some ions that will be formed. So when the vapor here diffuses downwards and reaches at this point where the temperatures are lower, we expect that the vapor will condense on the ions that will be at this point. So the vaporized alcohol condenses on the ions forming tracks. The tracks will be very well defined if an electric field is created by frequently rubbing the perspex lid of the chamber with a piece of cloth. The tracks obtained in the above cloud chambers vary according to the type of what? The radiation. And why is alcohol preferred to water? This is because alcohol is highly volatile and hence evaporates readily. Thank you. Thank you for that. Then we move on, we proceed. So those are the radiation tracks I was talking about. There are some tracks due to alpha particles and this is how they look like. If you look at those tracks, the tracks due to alpha particles are normally short. They are normally straight and thick. Very important points. They are short, straight, and thick. Why are they short? Alpha particles cause heavy ionization rapidly, losing energy, hence they are short what? Range. That is, when you're having an alpha radiation, these radiations will cause a lot of ionization. And during ionization, much energy is used. So when the energy is used, these alpha particles loses the energy and hence they cannot travel to a longer distance. They are massive, that is, they are heavy, and their path cannot therefore be changed by the air molecules. Haziwezi gonga gonga two sides by sides na hewa. And as such, the tracks come out being what? Straight. The alpha particles cause more ions on their path as they knock off more electrons. So when they're knocking off more electrons, more ions are formed, and that's why they appear to be thick. So each and every of these properties, shortness, being straight or thickness, depends on these factors that I have listed below. And then the other tracks, they're the ones from beta. These are the ones from beta, and you can see that there is a very great distinction between the ones from beta and alpha. The tracks found by beta particles are generally thin and irregular in direction. That is, they are not straight, but they're expected to be relatively longer than the ones for alpha. This is because beta particles being lighter and faster cause less ionization of air molecules. In addition, the particles are repelled by the electrons of atoms within their path. And to the last thing under this, the gamma rays produce scanty disjointed tracks. These are the tracks for gamma. Hata haziko connected, ziko disjointed. Hakuna kalaini hapo, they are appearing wavy. So gamma rays produce scanty disjointed tracks. The electrons ejected from the molecules behave like weak beta particles, hence the tracks appear the way you can see them. Thank you very much for listening from me. And I'm requesting that you can like the video, you can share the video, and you can even download the video for you to be able to watch later when you are offline. Thank you very much. I want to stop recording.